All right, today I will talk about Fourier analysis on finite non-abelian groups. Today I shall do for any general finite group that includes both abelian and non-abelian ones. So, Fourier analysis, whatever we have seen so far, that is for finite abelian groups. There we have seen that Fourier analysis starts with Fourier transform. So in order to extend the Fourier analysis on finite abelian groups to any general finite group, first we have to make sense of Fourier transformation there. So for that, let's first review what we have done in case of finite abelian groups. So we will quickly review what a Fourier transform in finite abelian group is. So for any finite abelian group G and a function from G to C, its Fourier transform is a function from the dual group which is defined as follows. So thus for every f I have f hat, and this correspondence f goes to f hat is linear and in fact an isomorphism between the vector spaces LG and LG hat. Furthermore, for we also see that for every for every phi and psi in belonging to LG, so the Fourier transform of the convolution is the product of the individual Fourier, as a pointwise product of their Fourier transforms. So that this linear isomorphism becomes an isomorphism between the algebras over C. Okay, because it's a linear isomorphism and it's a ring isomorphism as well. So the Fourier transform establishes a linear Fourier transform establishes an isomorphism between these two algebras. Okay, so this is this is the crux of what we have done for finite abelian groups. Now we will try to extend that to general finite groups. So I mean, it's not quite unnatural to expect that we might be able to extend all these even when G is non-abelian. But unfortunately, this is not the case. We have a serious problem. In fact, we can never have because of the following. Because if G is non-abelian, then there are functions defined over G which are not class functions. So thus LG is not ZLG. In other words, this algebra is not commutative, or I mean, an algebra being commutative means the ring is not commutative. So since this is not, so since when G is non-abelian, this is not commutative. So one can never expect to have an isomorphism between these algebras, because this one is non-commutative, whereas this one is always commutative, because here the multiplication is the pointwise product of complex numbers. Okay, so as what I was saying, that for finite abelian groups, the Fourier transformation establishes a bijection between them. And so if we wish to extend everything for general finite groups, so certainly we cannot do that, okay? Because these two structures are, I mean, when G is non-abelian, they are totally different, because one is, we cannot ever expect to have any kind of isomorphism between them, because one is non-commutative, another one is commutative. Okay, so therefore, if we want to extend the theory of Fourier analysis on general finite groups, at least we have to at least we have to give up this, because this one we cannot have when G is non-abelian. So we might be, in fact, we will be able to extend, but the extension, but in that way, in that extension, we have to certainly give up this. Okay. Now to define the Fourier transform in the setup of general finite groups, so as I have said that we have to give up the isomorphism between the group LG and LG hat. So we have, so since we have to give up that isomorphism, give up such an isomorphism for general finite groups. So if you want to extend, we have to first look at the same old Fourier transform in the set of a finite abelian groups from a different perspective, because this we cannot have for general G. This is very, very, I mean, now it's clear this is very, very special when G is abelian. In fact, that is why the Fourier analysis on general finite groups is not that simple. Okay, so this is very, very special for finite abelian groups. So if you want to extend the notion of Fourier transform for general finite groups, we have to first look at that from a different perspective. Then that will motivate us how to extend. All right, so let's see that. As I said that now I will look at the Fourier transform on finite abelian groups from a different perspective. So let's start with a finite abelian group G, and let chi1, chi2 up to chi k be all distinct irreducible characters of G. Since G is abelian, they are all one dimensional. In particular, they are all homomorphisms from G to S1. And then we obviously have the following. Well, so these are the according to the definition, these are all the members in G hat. So once we label them, so the labeling itself gives an ordering, that is the chi1 will come first, chi2 will come second, and so on. So once we fix an ordering of the elements of G hat, then every function in G hat can be realized as a tuple like this. There is a very small mistake that here it will be one more, so this parenthesis will be closed. However, it is clear that every function can be realized as a k tuple of complex numbers. Okay, and it's reversible. That suppose we are given a k tuple of complex numbers, then from there we can construct a function on G hat. So in view of this correspondence, we see that this algebra LG hat with respect to pointwise addition and pointwise multiplication is the direct sum of one-dimensional complex algebras, the direct sum of k copies of one-dimensional complex algebras. So this is easy. In fact, for any finite set of cardinality, let's say n, in the similar way, we have an isomorphism between Lx and c to the power n. Okay, so this is an isomorphism, and in the finite abelian setup, we have an isomorphism from Lg to Lg prime, namely the Fourier transform. So if we now compose this, so the composition of two isomorphisms over algebras, isomorphisms between algebras over C, is again going to be an isomorphism between algebras over C, and precisely that is the isomorphism. So it is from Lg to k copies of C, and if each f is being mapped to the values of each f being mapped to the tuple, where the ith component of the tuple is the value of the Fourier transform of f at the point chi I of G hat. So this is an isomorphism now. Okay. So you can say that why you may wonder why I am saying this, because it is nothing new. In fact, when G was any finite group, for that we have proved the following isomorphism, that is from the group algebra to the direct sum of matrix algebras, where these ni's are the dimensions of the irreducible representations. Let's write them by wi rho I. So in general, this is what we have seen. So of course, as a particular case, we must, I mean, as a particular case, we get this to our isomorphy. True. I mean, it's not uh, it's quite legitimate to raise the question that why I am talking about this, because this is nothing new. Yes, this is nothing new. The isomorphism is not, I mean, the fact that they are not isomorphic is not new, but something is new. What is new? New is the the particular isomorphism between this and that is new. Because the earlier isomorphism, I think I have also talked about that in one of the earlier videos, that earlier isomorphism was somewhat compositions of two further isomorphisms, and they are, I mean, the composition is not quite easy to see. Like you can, I mean, there are maps, abstract maps. There are maps. You are just taking the composition, but if you want to visualize what the composition, how the composition, I mean, if you want to visualize how the bijection is acting, that is very difficult to see. I mean, that is not quite natural. That's not quite, well, I should say that's not quite easy. But here we, uh, so here, I mean, again, let me repeat, the isomorphism of these two structures were known, but the new thing is this very particular isomorphism. So in particular, so in other words, Fourier transform is the very particular isomorphism between this and that. Now this is what we have seen for abelian groups, and for any general group, this is what we have. I know they are isomorphic. So from that, it is from that, like. Uh, in fact, I should, well, let me put it in this way. So for finite abelian groups, the Fourier transformation is the isomorphism between them. And for in general group, this is what we have. I know they are isomorphic. So if we wish to extend the Fourier transform in the general setup, so a correct approach should be to find a direct, so the correct approach for defining the Fourier transform in the setup of general non-abelian groups should be the following: that the Fourier transform should be defined in a way that establishes a isomorphism between this and that. Okay. So again, let me try to repeat that this motivates us to define Fourier transform in such a way that establishes an isomorphism between this group algebra and the direct sum of matrix algebras. Because as I have seen that, I mean, as we have seen that earlier when we talked about Fourier transform in the setup of finite abelian groups, there it used to be by isomorphism between the algebras LG and LG hat. So now we cannot extend that to find in general finite groups. So we have to, if you want to extend the Fourier transform, then we have to look at it in a different perspective. So we explored the finite abelian case, Fourier transform for finite abelian case a bit, and that shows that Fourier transform in fact gives an isomorphism between LG and the direct sum of k copies of C. Of course, we knew that they are isomorphic, but here the specialty is Fourier transform. Here the specialty is the very particular isomorphism which is given by the Fourier transform. And on the other hand, we know there is an isomorphism. We know that there is an isomorphism between them. So now from these two, it is very natural to consider the following: that if we want to extend the Fourier transformation for general groups, so we should do it in such a way that becomes an isomorphism between this and that. Okay, I hope this is now clear. Therefore, let's do that. So we'll start with a general observation. This says the following: that let G be a group and A be an algebra over K. A star is the group of units of A. So, well, I mean, throughout I assume the algebra is commutative. So I didn't mention that. So sorry. I don't need that to be commutative. Sorry. So ignore that. So the thing is, given an algebra, we can talk about S. Given an algebra A over C, we can talk about the group of units of A, which is a group with respect to multiplication of A. Now, if there is a group homomorphism from G to that multiplicative group of A, we now see that such a group homomorphism can be extended to a algebra homomorphism from LG to A. So what we should do is, so a typical element in the group algebra is F, which so F, you should recall that F can be written as a summation fx ex, and since we know each ex goes to phi x, so now if we want to extend phi linearly to, because G is the basis of LG. So if we have something on G, if we want to extend that linearly 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 to LG, so that it becomes an, now it becomes an algebra of homomorphisms, then this is the choice. And you can see that since we are talking about extension, this is the only choice. That is, if I define the following map for every A, that establishes a homomorphism between LG, a homomorphism from LG to A, and in fact you can see that that extends phi, because you can consider that x goes to ex. In this way, G is contained inside LG. So in that sense, this is an extension, and since G is a basis of LG, so therefore the extension is unique. So thus, given an F, there is a unique extension of phi to an homomorphism of algebras over C, and this extension we denote by phi tilde. Okay. So now it is quite clear to us that given a homomorphism from G to A star, then how to extend it to a homomorphism algebras from LG to A. So, in particular, we know that for each I, we have a homomorphism from G to GL of Wi, which is according to our notation rho I. So we can, so since it's a homomorphism from G to GL of Wi, we can extend that to LG. We can extend that to LG, and homomorphism of algebras between LG and endomorphisms of Wi, and so for each I we have such a homomorphism from LG to NWI, and so thus I have k such homomorphisms, and once we keep all these homomorphisms, in a tuple, that gives us a homomorphism from LG to the direct sum of endomorphisms of Wi, and this is the homomorphism. Okay, because coordinate wise the homomorphism was F goes to summation Fg rho Ig. That is how and that is what it becomes according to a general observation. So each rho I tilde sends of F to summation Fg rho Ig, and once we put them in a tuple, that gives a homomorphism from this to that, and this is the homomorphism. Okay. So and this is a homomorphism. Again, here whenever I'm saying homomorphism, it's a homomorphism between algebras unless otherwise said, because each row is a homomorphism from this algebra to that algebra, and then we are putting them in a tuple, so it is a homomorphism between algebras. Okay. So we shall now prove that this homomorphism between the algebras is in fact an isomorphism. Okay. Okay. For that, it is enough to prove that it is for that it is enough to prove that this is bijective. Okay. So so yeah. So to show this is bijective, I'm saying that it is enough to show it is surjective, because if you look at the dimension of both sides, here the dimension is order of G, here the dimension is endomorphisms of W1 has a dimension n1 square. So similarly, and any component, any ith summand will have dimension ni square. So the sum and dimension of the right hand side is summation ni square, which is order of G. So both the sides have dimension same. So it's a linear map from two vector spaces of same dimension. It's a it's a linear map between two finite dimensional vector spaces of same dimension. So it is injective if and only if it is surjective. So if once we prove that it is surjective, it will be automatically injective, hence bijective. Okay. So in order to show this is surjective, what we will do is the following. For each, what we will do is the following, that for each I, we fix a basis of Wi, and then once we fix the basis of Wi, so for each G, we can write down the matrix representation of the linear operator rho I G, and let this be the matrix. So well, let's not get confused. So the matrix of rho ig is Rij, which is so whenever a matrix A is given, we usually write the typical elements as A ij. So the matrix is denoted by Rij, which is written in this form. So a typical entry of the matrix will be rho ig alpha beta, where alpha beta runs from 1 up to ni. Okay. So now we have basis for each Wi, and whenever we have fixed a basis for each Wi, then the ring of endomorphisms or the algebra of endomorphisms becomes isomorphic to the corresponding matrix algebras. Okay. So thus the direct sum of endomorphisms of Wi is isomorphic to that, and the isomorphism is basically take a linear operator and write it and map it to its corresponding matrix with respect to the basis fixed beforehand. And once we have done that, so the surjectivity of the previous map that we were desired to prove, the surjectivity of this previous map is now equivalent to the surjectivity of this map, right? Here what we have done is from direct sum of endomorphisms of Wi, we just taking it, the matrix representations, we come here. So this map is now the composition of the earlier map together, the composition of the earlier map with the map that corresponds to the matrix representation of the linear operators. So since this and the endomorphism is isomorphic, and this map is just the composition, so this map is the composition of the earlier map with an isomorphism. So this is surjective if only if the previous map is surjective. Now how to show this is surjective? Okay. So what happens if it is not surjective? If that is not surjective, then the image will be a proper subspace of this, and whenever we have a proper subspace of a vector space, then we will have a non-zero linear functional defined over the vector space, which vanishes identically on the proper subspace. Okay. So assume that it's a proper, assume that the image is a proper subspace, then there will be a linear form, a linear functional from defined over this to C, so which vanishes identically on the image. Okay. Now it is very easy. So what is this? This is just this is actually just some copies of C. So therefore, this is just some Cm for some big enough M. So how will a typical linear function from Cm to C look like? So it means there will be a scale, there will be scalars A1 into Am such that the map will send Z1 up to Zm to ZA1 bar, I mean to yeah, so it will send each tuple Z1 to Zm to ZA1 plus 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 Z1 AM plus 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 Zm AM for every Z1, for every tuple Z1 up to Zm. And if the map is non-zero, then all AIs cannot be zero. So since we know the form of a general linear functional defined over this, from that we see that there exist scalars. So for each I and for each alpha beta, so all total there will be uh, so for fixing I, number of alpha betas will be ni square, and now I have ki, so therefore we will have n1 square plus 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 nk square, number of scalars not all zero, such that this becomes zero. This follows from the general form of a this comes from the general form of a linear functional. Okay. So this has, since and this has to hold for any r. Okay, fine. So there is a small mistake. Yeah, there is a small mistake. I will correct that. So what you do is you, I mean, there is a small mistake in the last line. Please ignore the last line. Rather look here. This is the correct one. Yeah. So basically, from the direct sum of algebra of matrices to from the a linear functional from an algebra of direct sum of matrices will basically a combination of all possible all the matrix coefficients, and since the non-zero functional is the functional is non-zero, but it vanishes on the image. So that means for every f, we have the following dependence relations on the matrix coefficients. Okay. Okay. So once this holds for every f, as I said that this is the correct one. This is not the correct one. Please ignore that. I will update that when I will send the PDF. So so this is what we get. Now we fix a j, a delta, and a gamma. Since this holds for any f, then so in particular, if this is our f, for that if this is our f, then for this f as well, this vanishes, right? So let's plug in this f in that expression, and this is what we get. Okay. Now let's try to observe that the left hand side, I mean, though it looks very complicated, but it's actually very simple in view of the relation between the matrix coefficients that we have established immediately after the Schur's lemma as a corollary of the Schur's lemma itself. So let's observe what this is. So this is so first of all we so this is what we had. So you can pull it outside the summation over g, so that this is now we are left with, and when j not equal to I, that sum, when I not equal to j, simply this will be 0. So the first observation is in this entire summand, the only thing that survives when I equal to j. Good. So when I equal to j, this is what we have, and then again we know what it is, right? So since we know what it is, so from that we know that the only term that will survive when delta is beta and gamma is alpha. So that shows this is just 1 by nj aj gamma delta, and from the relation that this is 0, so aj gamma delta has to be 0. So this is true for any j and delta gamma. So that shows all the scalars are 0, which is a contradiction because we assume that the linear functional is the non-zero linear functional. So now that shows the that shows that this map that shows that this map is isomorphism, or equivalently this map is an isomorphism. This map is an isomorphism. Okay, now we are almost towards the end of today's thing. We make a notation, we shall fix a notation and make a definition. So for any representation 0 of G and for any function f, so this is a linear operator from V to V, we shall denote it by f hat of rho. And with this notation, we shall now define the Fourier transform of Fourier transform in the setting of a general finite group. So for any given f, we shall define its Fourier transform by this tuple, which belongs to the direct sum of endomorphism algebras. And we have all, and once we write everything in this notation, and once we write in notation, then the f goes to this tuple is an isomorphism of isomorphism between in the group algebra LG and the direct sum of endomorphism algebras. Okay, because this is just the notation. So according to the notation, this is so f hat rho is just this. So therefore f hat rho 1 is the same thing when rho is replaced by rho 1, and similarly here okay. And f goes to this. We have already seen that that is the isomorphism between these two algebras, between the group algebra and the direct sum of endomorphism algebras. So keeping the similarity with the scenario of finite abelian group, it now makes perfect sense to define this. So define this as the Fourier transform of a function in LG, and thus what we get is the similar, as I said, similar to we will keep. I mean, we will, as I said, that we will extend the Fourier transform from finite abelian groups to general group finite groups. So now the extension is done, as likewise the finite abelian case. Even in the general finite group, Fourier transformation defines an isomorphism between the group algebra and the direct sum of endomorphism algebras. Okay, so now the Fourier transform is defined. Then we shall look for Fourier inversion theorem. So once Fourier transform is defined, this is not the natural thing that one can ask, that how to recapture f from its Fourier transform. So here also it is very easy. For any x and I, observe that rho I of x inverse f hat rho I is precisely this, because f hat rho I is summation fg rho ig. Once you apply the linear operator rho I f x inverse, this becomes this, because rho I is an homomorphism. Then we just compute this expression. So the trace times ni. So once you do that, so what is the trace of that? So the trace of this is so since this is this, so the trace of this is this precisely, and then we interchange the sum. So it will be a summation fg times this, and now we know what exactly it is. So we know what exactly it is. So yeah. So when g is exactly equal to x, only then this sum will survive. Otherwise, everything will be 0. So that gives us fx times, because when x is g is x, then this will be ni times ni square, summation ni square, which is in order of g. So this is what we get. So this becomes fx times this. And now once we divide the both sides by order of g, we get the following, that again you should ignore this line. Ignore, the correct thing is written here. I will remove that when I will update the PDF, upload the PDF. So this is what we get for any xg, that shows that how to recapture f from its Fourier transform. And here it is known as the Fourier inversion theorem. So I will leave you to, I will leave this to you to see that why this, why the Fourier inversion theorem of finite. So, well, sorry. So what I'm saying is, uh, as a since every time I'm saying that I'm extending the theory to for theory to general abelian general finite groups. So now I leave this for you to convince yourselves that why this implies the Fourier inversion theorem in the finite abelian case. Remember, for finite abelian case, a representation is same as its character, and their trace does not matter, and each ni is one. So once you consider them, you see this is exactly the Fourier inversion in the finite abelian. Then that becomes the Fourier inversion theorem of the finite abelian case. All right. So with the to summarize everything, we have extended the Fourier. We have extended the notion of Fourier transform from finite abelian groups to general finite groups. So like exactly similar to the finite case, Fourier transform defines an homomorphism between the group algebras LG and the direction of endomorphism algebras of the irreducible represent endomorphism and the endomorphism direction of the endomorphism algebras NWI, and then we prove the Fourier inversion theorem. Okay, with that I will stop.